Welcome back. In this video, we'll talk about functions of NumPy arrays. So functions are where NumPy really becomes something powerful and useful. We've seen already that we can access and manipulate arrays in various ways, but what NumPy is really here for is for crunching numbers. And doing functions of arrays are really where we start crunching numbers. So in this lecture, we're going to focus on entrywise functions. So functions that operate on each individual entry of an array independently. And then in the next lecture, we'll look at aggregation functions, functions that combine entries of arrays in various ways. Now, we've also seen a few mathematical operations on arrays. We saw addition and multiplication, and we even saw an example of a trig function. And in this lecture, we're just going to go into more details on how some of those things work. So as always, we'll begin by importing NumPy as NP. Looks fine. Okay, so now the first thing I'd like to do is create two arrays to play with. So I'll say big A is np.arange 1 through 11, and B is np.arange 11 through 21. So let's take a look at A and B here. Okay, so I see that A and B are both arrays. They have one dimension of size 10. A goes from 1 through 10, and B goes from 11 through 20. Okay, so the first thing we can do is negating an array. So let's just do something very simple. We're going to do minus A, and minus A does exactly what you think it should do. It takes all of the entries of A and throws a minus sign in front of them. Okay, so very, very simple, minus A. Another thing we can do is absolute value. So absolute value will remove minus signs if it encounters them. So for example, if we do np.abs, that's the absolute value function, np.abs, of minus A, we get back exactly the same thing as A because we added minus signs and then we took the absolute value and removed the minus signs. Okay. Entrywise binary arithmetic. So binary arithmetic means arithmetic that we do with two objects at a time. So let's use B now. So entrywise binary arithmetic, we can do A plus B, for example, and get the expected result. In a comment here, we've actually done this a few times before as well. We can also do A plus 2 and get the expected result. And the reason that that works is due to something called array broadcasting, which you'll be investigating in your homework. Okay. We can also do minus. Subtraction is just like addition. It just goes backwards. So in this case, we do A minus B. Each entry of A was 10 more, or each entry of B was 10 more than each entry of A. So A minus B is just an array of minus 10s. We can do multiplication. A times B does exactly what you think it should. It multiplies all of the entries entry-wise. So for example, this last entry here of 200 is 10 in A times 20 in B. We can do division. A divided by B gives me an array of floating point numbers this time. Because NumPy noticed, hey, not all of these numbers cleanly divide, I'm going to give you floating point numbers here. In this case, for example, this 0.5 is 10 in A divided by 20 in B. Continuing along with the mathematical circus, we can do entry-wise exponentiation. So for example, here's each entry of B raised to the corresponding power in A. The numbers get very big here. So for example, this final item here is 20 raised to the 10th power. Okay, and we can also do modulus. So you know me, I love my modulus operator. So let's do B mod A, and we can see, okay, these are all of the remainders when we divide B by the item of B by the corresponding element of A. Okay, so binary arithmetic, really nice and simple. The syntax is exactly how you'd expect, and the behavior is entry-wise. So this makes it really convenient to add, subtract, multiply, mod out, anything along those lines using arrays when you want to operate entry-wise. So whenever you're operating entry-wise, think about using array arithmetic. Of course, we can do better than just arithmetic. We can do mathematical functions as well. So let's do an example. Let's do some trig functions. So I'll take theta equals np.linspace. I want to do a couple points between 0 and pi. So np.pi gives me the mathematical number pi. So if I construct this array, I'll see that I have 0, pi over 2, and pi itself in my little 3-element array here. And now let's do a few examples. So I'm just going to add some print statements to make this nice and visual. So print theta equals, and then here's theta. And then I'm just going to make a few copies of this. So let's do sine of theta as our first function here. Let's do cosine of theta as our next one. And let's do tan theta as well. So we're going to do sine, cosine, and tangent. So we have np.sine is our corresponding function that we apply to theta, np.cosine, and np.tangent. So now we're going to print out the result of applying a function to theta for each of sine, cosine, and tangent. So here we go. We have 3 arrays, each of which have size 3, where we evaluate sine, cosine, and tangent, each at 0, pi over 2, and pi over 4. If you remember from pre-calc, you'll know, for example, that sine of pi over 2 is 1, and that's indeed what we observe here, whereas sine of pi is 0, so this is pretty much what we would expect. Okay, so trig functions in NumPy work exactly like you'd expect. Okay, next, exponentials and logarithms. So let's do another example here. I'll make a new array x. X equals np.array. Let's just do 1, 2, 3. Nice and visual there. So there's x. We can do lots of things with x. So for example, we can exponentiate a scalar. We actually saw exponentiating an array above, but we can also exponentiate scalars, no problem. So the result of 2 raised to the power of x is 2 to the first, 2 to the second, and 2 to the third, all in an array. NumPy provides an exponential function. Okay, so NumPy np.exp will give you e raised to the x for any given value of x. So here we are, we have e to the first, e to the second, and e to the third. If you remember, e to the first, or just e, is about 2.718, so that looks pretty good. We can undo the exponentiation operation with the natural logarithm, so np.log of x. If you just do log with no other information, you always get the natural logarithm, and that's because the natural logarithm is hashtag the best logarithm. Okay, so natural logarithm, hashtag best logarithm is very easy, np.log. If you want something less good, like np log 2, so that's the base 2 logarithm, or we can also do np.log 10 is the base 10 algorithm. So those logarithms are not as good as the natural logarithm, and I will die on this hill. But if you need them, you can get them using np.log 2 and np.log 10. Okay, so sometimes when you're working with NumPy, you'll perform an illegal mathematical operation. And in this case, NumPy will not usually give you an error, but it might give you a warning, and it will usually generate an np.nan. The nan stands for not a number. So a very common example of this is when we are computing the logarithm of negative numbers. So let's do an example. I'll make a new x equals np.array -1 and -2, nice and simple. So here's x, and here's np.log x. Of course, I'm using np.log for natural logarithm because hashtag best logarithm. So now, when I run this code, I see that I get a copy of x. I see that I get an array. The array has 2 nan values rather than 2 numbers. And you'll see that I've obtained a runtime warning. And the runtime warning says invalid value encountered in log. What this means, this is NumPy speak for, hey, dummy, you tried to take the logarithm of a negative number. And the way this manifests in my code going forwards is that now I have this array that contains nan values, not a number. Now, nan values propagate, okay? And what that means is that if you try to do any operations with nan values, you'll create more nan values. So for example, here's the natural logarithm of x again. I've stored it in a variable y. And now if I try to do something new, like say I'm going to add y plus x, okay, so we know that y plus x is a thing we can usually do. Here I'm going to add y plus x, but the result of adding y plus x is an array with nans again, because NumPy said, hey, I don't really know how to add nan to a -1 and get a reasonable result, so that is also going to be an nan, and similarly for the second entry. So nans propagate. Whenever any one of them shows up in a computation you're doing, it will cause the output of that computation to be nan as well. A similar case that is not quite the same is when we try to divide by 0. So let's take a quick example here. I'll do z equals np.array. I'll just take 1, 1. And I'll try to divide this by np.array 0, 0. And let's check on z. So here I got another runtime warning, and it says divide by 0 encountered in true divide. This is NumPy speak for, hey, dummy, you tried to divide by 0. And what this gives me is an array with 2 values, and both of those values are equal to inf. So the inf value, as supplied by NumPy, also propagates. So for example, we can check that z plus 1 is also inf. So that makes sense. There's something a little bit different with inf compared to nan, which is that we can divide by inf values. So if I do 1 over z, for example, I divide 1 by infinity, and I get 0. So I won't always have an inf result from any computation involving an inf. If I divide by an inf, I can get 0, a nice normal number again. On the other hand, if I try to divide by nan, so for example, if I try to do 1 over np.array, and I'll just do np.nan here by hand. If I try to divide that by, if I try to divide 1 by nan, I'll get nans rather than 0. Okay, so we've talked about a lot of ways to apply mathematical functions to NumPy arrays. We've been working with one-dimensional arrays, but all of this works equally well for two-dimensional arrays. And I'd like to illustrate this by using NumPy to plot some functions. We'll plot both 1D and 2D arrays with our plotting methods. Now, we haven't formally talked about plotting tools yet, so I'm going to ask you to not worry about the plotting tools. We will be getting to those very, very soon. But just focus on the array manipulation and focus on looking at the plots and seeing, oh yeah, this is what I would expect from math class. Okay, so in order to use our plotting tools, we're going to import matplotlib. From matplotlib, import pyplot as plot. You'll be seeing this little line of code over and over and over again because we're going to be using matplotlib all the time. Okay, so let's make a parabola. So we are going to create on the x-axis, we'll do np.linspace from -1 to 1, 101 evenly spaced entries. So recall what this is. This gives me evenly spaced entries, in this case 101 of them, between the two bounds -1 and 1. So I can do x, and then I can easily do x squared. That's a perfectly valid array manipulation. We've seen that before. I can raise an array to a power, no problem. So let's plot x and x squared. And here's my parabola. So this is an indication of how powerful NumPy is. We can get very nice mathematical plots by just creating an array and applying our mathematical functions to that array. No for loops, very simple syntax, and we just have a plot in 2 lines here and then 1 line to load in matplotlib. So we can do very powerful, very efficient and fast stuff using the NumPy library here to get mathematical functions, visualize mathematical functions, and see the results. Let's do another example. Let's do exponentials and logarithms. So in this case, I'll use the same x. So let's plot x and np.exp of x. And I'm just going to give that a label. We'll talk about labeling shortly. So I'm just going to give that a label, y equals e raised to the x. OK, so if I run that, I'll see that I have my function, but not my label, and we'll see why in a little bit. Now let's add to that. I'm going to add plot.plot x np.log of x. So np.exp of x, np.log of x, hashtag best logarithm. 1, okay, we'll give this a label as well, r. And notice these are raw strings, similar to when we were working with regular expressions. And then finally, I'm going to add, let's just actually run that real quick. Okay, there we go. We got some runtime warnings because we did try to take logarithms of negative numbers here. That's what would have been back over here, but isn't. And now finally, let's just add a legend so we can tell them apart. So plot.legend. Okay, here we go. So this is a reasonably nice mathematical diagram now. We were able to plot 2 functions and give them labels to tell them apart very, very simply. Now, the magic here, again, is really in the NP or NumPy handling of arrays, okay? We're able to apply a mathematical function to every element of the array using just a single function call, no for loops, no anything. Finally, I want to illustrate computing functions over 2D arrays in order to illustrate plotting, so two-dimensional plotting. So when we do two-dimensional plotting, we have a two-dimensional set of numbers. We compute the function in each one, and then we plot that in a way that's often called a heat map. So let's take a look at how this works. So I'm going to create two 100 by 100 arrays. So let's do x equals np.reshape. You don't have to worry about what exactly these arrays are at the moment, although this should be familiar to you. I'm not using any functions you haven't seen so far. So I'm going to have x be equally spaced values from 0 to 2 pi, and I'm going to have 10,000 of them. And I'm going to reshape that into a 100 by 100 grid. I'm going to have y be similar, but I'm going to use .t. This is the matrix transpose, if you will, and I'm going to call that y. So let's just first see what x and y are. So imshow lets me visualize these. If I check on x, I can see, okay, what I've got here is numbers that are decreasing as I go down. If I check on y, on the other hand, I'll see, okay, I have numbers that are increasing as I go right. If you want to get a legend here, we can add a color bar. So this tells you what the colors mean. Okay, so now what I'm going to do is I'm going to plot a function of x and y. So we're going to do z equals np.sine of x plus the cosine of y. And I will just check on z real quick. Okay, so z looks like a two-dimensional array, makes sense. I can check on its shape. Looks like z is 100 by 100, just like I would expect. And now I can do plot.imshow z, and let's add a color bar just for legibility. So now I have this nice, attractive-looking plot of a function. So the colors tell me the values of this function z, and then I have the x and y pieces that I use to create this function that are not shown in the plot, but they're what lies underneath and gives me the ability to do this by applying a single function to multi-dimensional arrays and plotting the results. We'll go into much more detail about plotting and into much more detail about plotting 2D functions, including some ways that are smarter and more sophisticated than this in a coming lecture. For now, I just wanted to illustrate to you that we can easily apply NumPy functions over multidimensional arrays, and then if we want to, visualize the results. Okay, in the next lecture, we're going to look at aggregation, functions that allow us to combine numbers in NumPy arrays and get various kinds of results. So stay tuned.